industrial structures, refineries, and more. He published more than 80 papers reflecting his experience in geotechnical practice. He was awarded IGS Delhi Chapter Lifetime Achievement Award and IGS Dinesh Mohan Award for Excellence in Professional Practice. He delivered 6th Madhav Lecture on geotechnical investigations in difficult ground conditions. He has delivered keynote lectures in Indian geotechnical conferences and other forums. He was the chairman of IGS Delhi chapter and was IGS Executive Committee member for 2 terms. He is a member of several BIS code committees and IRC D3 and H4 code committees. He strives to integrate field practice with academic research to be responsive to complex geotechnical challenges facing our country. Some of major projects that he involves include the Central Vista Project, New Delhi, several wind turbines in Khavda district, Kutch, Gujarat, Sri Ram Janmabhoomi Temple, Ayodhya, and more. We are truly honored to have such a towering personality and a respected geotechnical practitioner among us. Today, Mr. Ravi Sundaram will be addressing us on topic planning geotechnical investigation works for small, medium, and large projects. Before we begin, a quick note for all participants. If you have any queries, please post them in the chat box. All questions will be taken up and answered during the Q&A session at the end. Alternatively, you may also raise your hands during the Q&A session. We'll unmute your mic and give you an opportunity to ask directly. Now, I warmly invite Mr. Ravi Sundaram to kindly take over and deliver the talk. Over to you, Ravi Sundaram ji.
Thank you very much. My pleasure to interact with all of you at IIT Tirupati. I am now going to share my screen. Please is my screen visible to you? Is my screen visible?
Sir. Yes, sir.
It's visible. Thank you very much. Something happened. Yeah. So I will be talking on planning geotechnical investigations for small, medium, and large-sized projects. I am very grateful to IIT Tirupati for inviting me to make this presentation. It's been a very special association I've had with IIT Tirupati. Dr. Janki Raman, Professor Ayoti Raman, and all have been very close to me. And it's really an honor to be interacting with the students of IIT Tirupati. Now I start by comparing the civil engineering project with the human body. Just like you have various parts of the body, there are various components of the project. With advancement in technology, we have specialized experts for various components. Just as for the heart, you have a cardiologist. For the foundation, you have a geoprofessional. A geoprofessional includes geotechnical engineers, geologists, geophysicists, the entire list. This is what I'd like to do when I want to explore the ground. Go down and see really what's there. But since practically such a thing is not feasible, now we have to resort to geotechnical investigations, which you know is a vital part of all geotechnical studies. It generates the most important parameters, the field and laboratory data for the foundation design. It's a prerequisite for economical and safe foundation design. The basic concept is that whatever is envisaged at the investigation and design stage should translate into construction that is in sync with the design concepts, the assumptions made, and the predicted foundation behavior. Today, demands of fast-track projects requires that engineers should come up with solutions for complex problems in minimum time. So we have to respond quickly to keep pace with the demand of fast-track projects. Next is that the design parameters have to be more realistic. You cannot go with the conventional approaches and give very conservative design values. You have to stretch your values because the loads are now high, the demands are high. Therefore, innovation, safety, and economy, all these three must go hand in hand. In the recent years, there have been significant advancements in geotechnical investigation methods. There is a shift from the traditional investigation methods of boreholes only to modern investigative methods, particularly in major industrial structures which are heavily loaded, tall buildings and multi-storied buildings, commercial projects. All these various modern techniques have revolutionized foundation design. So this includes adoption of advanced, sophisticated in-situ testing techniques, like the electric cone penetration test with pore water pressure measurement, SPT energy transfer measurements, pressure meter, cross-hole seismic test, seismic cone penetration test, and various other geophysical tests. Now, primarily, digital data acquisition is becoming very popular, and all these are very effective for site characterization and to identify the subsurface conditions, and particularly identify critical geotechnical issues. They help generate reliable geotechnical parameters for superior foundation design. In many cases, it does yield higher SBC values than what you would get from a conventional investigation. In situ tests, these are what are the way to go now. They supplement the borehole data, provide additional information for foundation analysis, and help you validate the design. Now, what are the benefits? You have enhanced accuracy and reliability. There is a minimization of sample disturbance. It provides you with a more accurate representation of the soil properties, soil and rock properties, such as soil strength, shear strength, the load displacement behavior, in-situ density, in-situ permeability, various other parameters. Faster results, reduced delays. You can make timely adjustments. Decision making is fast and more correct. So you can shorten the timelines, minimize delays. There is an improved risk assessment. You can identify potential risks such as ground instability, liquefaction during earthquake, possibility of bearing capacity failure, excessive settlement, etc. It also leads to a better understanding of soil behavior. It can provide valuable insights into the behavior of the soil, which is crucial for designing the foundations, slopes, and other geotechnical structures. If you have a reduced sample disturbance, it gives you better assessment of the ground behavior, eliminates those errors. And there are a wide range of applications, such as site investigation for foundation design, slope stability analysis, earthquake engineering. So it's a valuable tool for ensuring the safety and stability of the structure. Now let us look what kind of tests are popularly used. Of course, the conventional tests are the plate load tests. Now, footing load tests are also being performed on large size foundations. Field permeability tests and aquifer pump out tests These are also performed on site. Now, the advanced techniques which I was referring to, SPT energy transfer measurement, pressure meter test, electric cone penetration test with pore water pressure measurement, seismic cone penetration test. All these are very useful tests and help you make a better assessment of your foundation behavior. So just a slide showing the various kinds of in situ tests which are available and the kind of benefit that you can get from performing these tests. I am not going to very close go through this in detail. I move on to geophysical tests. Geophysical tests not only help in establishing the continuity of strata, but it also enhances the quality and reliability of the investigation. It reduces the likelihood of encountering unforeseen ground conditions during construction. So by fusion of geotechnical and geophysical data, a combined geotechnical cum geophysical model can be developed for effective site characterization. So this helps you identify stratigraphy and ground profile over large distances. For example, metro construction, where you have a long alignment, you do boreholes at specified locations, but in between you need to know the continuity of the strata. It confirms the design parameters for foundation analysis and also helps in your liquefaction analysis during seismic loading. So the most popular geophysical tests which are used are cross-hole and downhole seismic test, seismic cone penetration test, seismic refraction test, electrical resistivity test, electrical resistivity imaging. There is also the SASW and the MASW test. MASW is getting very popular these days. So the aim with all this has to be to collect good quality data so that adequate and accurate information is available about the strata. So in situ tests can greatly enhance the quality of the data and help predict your foundation behavior reliably. This can have far-reaching effects on the design and construction or even during the post-construction periods. Shortcut methods of investigation can always will always increase the risk of foundation distress and life of the structure. Therefore, you should aim to perform appropriate tests through a thorough soil investigation so that you can reduce the risk of failures. So let's all work towards minimizing these risks and improving the overall engineering performance of all structures. Now let us look at the various levels of geotechnical input which can be made available. So this is called the geotechnical investigation pyramid. Starts from bronze and goes up to silver, gold, and platinum. So as you move up along this pyramid from bronze towards platinum, your factor of ignorance reduces. I'm not talking about factor of safety. I'm talking about your ignorance level has reduced. Therefore, you are more informed. You are ensured, you're sure that what kind of strata it is. So reliability of your design is enhanced. Once that is done, there certainly will be reduction in the foundation cost and reduction in the construction time. At the same time, you minimize the possibility of failure. So, of course, as you go from the bronze to the platinum, the cost of the investigation will increase. But finally, it boils down to the commercials that you get what you pay for. So let's look at these various levels, bronze, silver, gold, and platinum. So in the bronze level, you have shallow boreholes, very limited testing and sampling. Uh, as you go to the silver, at least you do boreholes deep enough below the pile tip. Uh, when you go to the gold level, of course, you do more uh, testing. You do in situ tests, lab testing for complete range of lab tests. Uh, at the platinum level, of course, you would supplement it with pile load tests, dynamic pile load tests, etc. The geotechnical engineer in the bronze level may be a limited experience, non-expert, whereas in a gold and platinum level, you have experienced experts. The design parameters in a bronze level is guessed. Gold level, you have site-specific to enhanced site-specific. The analysis in a bronze level, really nothing much, only thumb rules. Whereas gold and positive platinum, you have detailed theoretical analysis, maybe advanced numerical modeling. Design rules, the design is just thumb rules as far as a bronze goes. And you can move on to a serviceability based, optimized serviceability based criteria. The foundation design in the bronze, I don't know, it may be oversafe, it may be impractical or even unsafe. Whereas at a gold level, you have much reliable, optimized designs, practical to build, safe. You have savings in cost and time, and you can be very sure that your structures are safe. The risk at a bronze level may be quite high, whereas gold and platinum level, you have very low risks. Obviously, the cost of investigation will increase as you move from the bronze to the platinum. But the basic idea is that the additional cost would be much very small compared to the amount of savings in foundation cost that you do. So let us look at the various stages of the investigation. You have a preliminary investigation. This is for site selection, making cost estimates, initial planning. So you want to do just get an idea of the geology of the area, which whatever is published in literature, GSI maps, etc. Data from investigation of nearby structures can give you quite a lot of information if it is available. A site reconnaissance, you can physically go down and see what the site conditions are, whether any rock is exposed at any place. Performance of nearby structures, if you can see nearby structures, if there has been a failure or anything like that. As far as river bridges are concerned, scour depth is an important criterion. So that's you should be able to obtain. As far as the detailed investigation goes, you want to determine the engineering characteristics of the soil and rock, the properties of the various layers, their engineering properties, the depth of the water table, establish your design parameters, which influence the choice of foundation type. Then, of course, you assess the bearing capacity for piles, for open foundations or well foundations, pile load carrying capacity, and all that. The construction stage, you might want to reconfirm design parameters in some very critical cases for major projects. So you can confirm the characteristics of the properties, whatever was assessed during the detailed investigation. You may conduct some in situ load tests. Pile load tests are often done to verify that the pile is safe under the design load. And finally, decide whether the design basis on the basis of the detailed geotechnical investigation done, that is acceptable or not. If required, you may modify and redesign the foundation system. So planning the investigation as such is an interactive and site-specific process. It requires some brainstorming. Have a look at the site and then take your call on what you would like to do. So let us see what are the various components here. You would start off with a desktop study, analyze the geological conditions, inspect the site, look at the soil and rock samples, do a reconnaissance study, then do the field investigation, follow it up with laboratory testing on the undisturbed samples, the disturbed samples. So you must know what various lab tests are to be conducted. And once that is done, you can do the interpretation of data and prepare the geotechnical investigation report, giving your recommendations on the bearing capacity, settlement, etc. So let's look at these activities in detail. The desktop study, you are going to study from published maps, Google Maps or aerial photos, get an assessment of the type of soil and rock formations in the area, the geology of the area, any natural resources are present, seismic activity in the area, what is the pattern of streams and rivers in the vicinity of the area, groundwater level at nearby sites, or published reports of the Central Groundwater Board. All this can, you should be having this information before you go to the site for a reconnaissance study. So in the reconnaissance, you would have a look at the soil and groundwater conditions, the topography, the drainage pattern, the vegetation. All these can give you an idea of exactly what's going to happen here. Condition of existing structures may be useful. Suitability of the site for the proposed project, you will have to assess that based on your desktop study and your reconnaissance before you give the go ahead on let's go and construct here. The field investigation. So this should obviously be, the scope of this should be decided based on the project size, the importance, and the specific requirements of your project. The structure details should guide you regarding this to decide on the extent of investigation required, whether you need to do a simple investigation or a detailed, thorough investigation. Also, site conditions, topography, nature of deposits, groundwater depth, depth of rock, various parameters you would have to look at. Of course, what is the earthquake zone in the area? So you would get that from the IS code or the Vulnerability Atlas of India. Make an assessment of the likelihood of liquefaction, so that then you can make decide on the investigation depth. So for small projects, you may be doing a few shallow boreholes, 8 to 15 meter depths, a few trial pits maybe. Going for medium projects, maybe boreholes to 15 to 25 meter depth. It could be anything between 5 and 25 boreholes. Cone penetration tests are optional. It would be very good if you can do it because it gives you useful data to economize your design. Large projects, of course, you should be doing deep boreholes. CPTU should be done. Pressure meter tests, preferable. And in-situ tests such as field permeability, particularly if you have to do dewatering, plate load tests, geophysical tests, all these will help you get the right parameters for your foundation design, your liquefaction analysis, etc. Next is the laboratory test. Once the field work is done, you have disturbed samples, undisturbed samples. So on the disturbed samples, you have soil gradation, Atterberg limit, specific gravity, free swell index. Particularly if there is a swelling expansive soils at the site, free swell index becomes critical. Undisturbed samples, density in moisture content, shear tests, direct shear tests or triaxial tests. Triaxial tests could be CU or CD, CU or CD. Consolidation tests, swell pressure, laboratory permeability tests. All these tests should be performed on depending on the project requirement. Then if there is filling and roads, etc., you might require a standard Proctor test or modified Proctor tests, lab CBR, relative density, etc. Then chemical tests. Most commonly performed tests are sulfates, chlorides, organic matter, pH value, harmful salts in soil and groundwater, etc. Data interpretation, engineering analysis, and report is the last phase. So this should contain your geology, your stratigraphy, your groundwater conditions, likelihood of groundwater level rising, presence of loose or soft zones. Do your liquefaction analysis depending on the earthquake magnitude. Decide your foundation type and depth, and then provide with the foundation recommendations. For shallow foundations, you will require bearing capacity, the design bearing pressure, shear criteria, and settlement criteria. Pile capacities, if piles are required, and if ground improvement is required, then the type of ground improvement method which would be suitable for this particular project. And finally, you need to give in your report the foundation construction aspects. If you are doing excavations, what should be your excavation slopes? If you're going to be doing the foundation dewatering for foundation construction. Similarly, if the chemicals in the soil or groundwater are high, then what kind of protection measures need to be taken? So now, before you actually go and start the investigation, you should prepare a layout plan of the building or bridge or whatever you're constructing. Along with for bridges, even the approaches should be clear as to what is the alignment. For buildings, you should know the number of stories, the heights, basements, etc. For bridges, alignment map showing the location of the piers, abutments, and embankments, etc. For heavy industry, power plants, the layout plan should show the various facilities, assess the loading conditions, identify the heavily loaded structures, decide on the location for boreholes and field tests, decide on what in-situ tests you want. SPT, vane shear test, you would do it on soft clays. Also plate load tests. Cone penetration test, seismic cone penetration test, a dynamic cone penetration test, pressure meter test, various other geophysical tests, like maybe cross-hole or downhole seismic test, etc. Collect and assess the available bore log data and soil characteristics. Make an assessment of the geotechnical risks, seismic risk, liquefaction potential, slope stability, particularly for deep excavations. Nowadays, tall buildings have 3 to 4 basements. Also, metro construction requires deep excavations. So, scope of the investigation. So, for buildings, the exploration should cover the entire area of the building and surrounding areas. The approach roads and internal roads within the plot may also have to be investigated. For bridges, the exploration should cover the entire length of the bridge, its approaches, and the embankments. As far as industry is concerned, industrial structures, all important structures need to be covered. The depth of investigation. should be decided based on the expected stratigraphy, the depth of rock which you expect, the topography, the local conditions. If scour is expected, you have to go sufficiently below the anticipated scour depth. Of course, you should be aware of the type of foundation that may be required, the depth of the foundation, the loading conditions, presence of superficial fill or unsuitable materials. Like, for example, at the Ayodhya temple, Ram Janmabhoomi temple, we found fill to more than 13, 14 meter depth. The depth of the investigation should be at least 1.5 times the foundation width, preferably 2 times. For high embankments, the depth of investigation again should be 1.5 to 2 times the height of the embankment. If loose, weak, or unsuitable soils are met, you might want to increase the depth of investigation, go down sufficient depth into the firm or stable soils or the underlying rock. Number of boreholes which you need to do. So this becomes an important question. How many boreholes should be drilled? How deep should you drill it? So let us look at the various codes. The Euro code says that it should be 1.5 to 2 times the foundation width, or to competent stratum, and also 1 borehole per building, grid-based coverage depending on the variability. So it would be approximately anything between 20 to 30, 40 meter grid. IS 1892 also says 1.5 to 2 times the width, or until hard stratum. For multi-storied buildings, it has to be deeper, a minimum 30 to 40 meters. And also for large sites, at least 1 per 250 to 500 square meters, minimum 3 per building. So these are all basic thumb rules. Your British code says explore the full depth of stress influence, deeper if variability is present. Boreholes at the corners and center of the building footprint as a minimum. ASTM has no prescriptive depth, depends on the geology, the groundwater, and the project risk. The numbers are also flexible depending on the structure type, geology, and the hazards. So let us look at this chart here. The purpose of the boreholes and the various tests is to identify the soil types, the layers, their mechanical properties, their engineering properties. You estimate the bearing capacity, assess the groundwater level, recommend the soil suitable foundation type, detect potential issues such as differential settlement, expansive soil, etc. And the required depth should be maximum twice the width of the largest footing or a competent bearing strata, like a rock layer, typically ranging from 15 to 30 meter for a large projects. So a number of boreholes again, say for small projects, you would have 1 borehole per 250 to 500 square meters. For larger sites, boreholes every 20 to 30 meters grid. Also, the type of structure is important. Heavy or high-rise buildings require more boreholes. Critical facilities like hospitals, power plants, bridges, etc. need a very detailed investigation. If there is soil variability, additional boreholes are required if the initial investigations show inconsistent results. Follow the design codes and take your call. So the common tests which are conducted for stratigraphy with detailed logs So the borehole with detailed logs, test results and soil classification, groundwater level, and various other assessment of risks and mitigation measures. So let us look at the depth of investigation. A 4 5-storied building without basement, say area less than uh, um, 500 square meters. Maybe 1 to 2 boreholes to 12 to 15-meter depth in soil. If rock is met, then you might want to drill additional 3 meter into soft rock or 1 meter into hard rock. 6 to 15 storied building with one basement, you might want um, 5 to 10 boreholes to 25 meter depth or so for open foundations or raft foundations. Drill minimum at least 5 meter into soft rock or 3 meter into hard rock. If you're planning piles, then the borehole should be at least 30-meter depth or at least 10 meter into 10 meter below the pile tip. It's preferable to include CPT for medium-sized buildings. So these are just guidelines. Please decide based on the site conditions. If there is loose fill or unsuitable material, or the soils are prone to liquefaction, then you might want to increase that depth. Now I come to tall buildings, height more than 50 meters, housing complex, commercial complexes, 15 to 50-storied buildings, 1 to 3 basements. So here you need a more detailed investigation, maybe minimum 3 boreholes to 30 to 60-meter depth per tower, preferable to do minimum 2 CPT per tower to at least 30-40-meter depth. Pressure meter tests per tower, cross-hole seismic test or downhole seismic test, or seismic cone penetration test should be done at least for 2 to 3 in the project. Now, if rock is met, then you would like to do at least 10 meter into soft rock or 5 meter into hard rock. Again, CPT should be done to refusal. Pressure meter tests are preferable, and cross-hole seismic test also. Again, as I told you, these are guidelines. Now we come to bridges. So I have minor bridges and underpasses where soil is there maybe 15 to 20 meter deep or 2 times the foundation width. If there is rock, of course, you want to do at least 5 meter into soft rock or 3 meter into hard rock. As far as major bridges, ROBs, grade separators, viaducts, and all are concerned, here you have to be a little detailed. 30-meter depth for open foundations, 40-meter depth for piles, but minimum 10-meter below the pile tip. If cover is likely, then you have to increase the depth accordingly, and preferable to include CPTU at least at every alternative pier location. If rock is met, of course, I need 10 meter into soft rock or 5 meter into hard rock. And pressure meter tests should be done to assess the soil and rock characteristics. It would be a good idea to include CPTU at every alternative pier location. Now, if we come to high embankments, soil at least 1.5 to 2 times the height of embankment, preferable to include CPTU at every 100 to 150 meter along the alignment. Rock, of course, I need 3 meters into rock, whether it is soft or hard. Again, as I told you, these are guidelines. Now I come to industrial structures. There could be light industrial structures, sheds, G plus 2 to 3 floor kind of structure. So here you may require uh, 15 to 20 meter deep boreholes, at least 2 B below the foundation level. If rock is met, again, we would like to go at least 5 meter into soft rock or 3 meter into hard rock. As far as heavy industry, power plants, cement plants, refinery, all these kind of heavy structures are concerned, you would probably go for 25 to 30 meter deep boreholes and, for open foundations and 40 meter deep for piles. Again, minimum 10 meter below the pile tip. CPTU to minimum 30 meter depth, 2 to 3 per heavily loaded structure, preferable to perform pressure meter tests for critical structures, and geophysical tests like cross-hole downhole seismic or seismic cone penetration test will help you do the liquefaction analysis, etc. Again, for where rock is met, you would like to do at least 5 meter into rock for open foundations, and again 40 meter or 5 meter into rock, minimum 10 meter below the pile tip. Then CPTU up to the top of the rock, pressure meters for critical structures, and geophysical tests. Now let us go to the in-situ tests. Standard penetration test, usually performed as a routine practice in all soils at 1.5 to 3 meter depth intervals. Field vane shear is performed in soft clays. Field permeability test, this is performed if there are issues related to dewatering, water seepage, etc. You would do a falling head test if it is cohesive kind of a soil with low permeability. Constant head test if it is high permeability sands. In rock, you might want to do it with packers. So I come to boreholes. The typical the IS 1892 was revised in 2001. So this includes these are mechanical shell and auger rigs. This is the light duty rotary rig. These identify your soil types, the index and engineering properties. You assess the groundwater level, estimate bearing capacity, recommended a suitable foundation type, detect potential geotechnical issues. So I come to SPT. So this is the SPT using an auto trip hammer so that the height of fall remains fixed. Have a video here. You can see the auto trip hammer. It helps you ensure that the height of fall remains fixed. Mm. So you transfer maximum energy to the anvil. Now I go to rock drilling, rotary core drilling through a rock to get good quality cores. So you should be doing hydraulic rotary core drilling with double tube or triple tube core barrels for obtaining good quality rock samples. So if you would like to get a rock of this quality, identify clearly the crushed zones and the jointing pattern, you should be using a hydraulic um, rotary drill machine using a double tube or triple tube core barrel. The triple tube gives you much better quality samples. The drilling bits used, a soft rock, you would use tungsten carbide bits. In hard rock, you would use diamond widths. Next, I move on to SPT energy measure. Now, this is the SPT being conducted. This is the SPT analyzer. The N value has to be corrected for the overburden pressure, the dial latency, efficiency of the hammer. Normally, 60% is the standard reference. The borehole diameter, the sample type, rod length, and the fines content. So you have an instrumented rod which is inserted here. Uh, so the SPT analyzer is furnished with a 0.6 meter sub-assembly of an SPT rod, instrumented with the two calibrated strain gauges. On the side, two accelerometers are bolted to the rod section. The instrumented rod is then inserted at the top of the drill string. And once you do this, you will be able to get the energy transfer detail. SPT energy calibration can normalize the energy transfer to the SPT head and standardize the result. It will remove the scatter in the values and enhance the reliability of the data. Energy calibration should be made for each rig, which will have different type of driving systems and skill operator. Non-standard SPT systems may deliver variable energy. So then if N values would not be realistic. So we want to correct it to standardized 60% energy transfer. So all the parameters, whether it is bearing capacity, settlement, other geotechnical parameters which are estimated on the basis of average N value, you need to be at 60% energy transfer. Also, the liquefaction potential should be estimated based on the N60, as it is called, corrected to 60%. Low energy will yield high N value, leading to unsafe predictions. High energy transfer could result in oversafe design. The IS 2131-2025 recently been released. It recommends energy transfer measurement. The field vane shear, I will not go through it in detail. This is the standard vane diameter, 2 times the diameter is the height of the vane. So this is the test being done. This is at Kochi Metro. This is the borehole and the field vane shear test. Quickly, about plate load tests, commonly used for routine geotechnical investigations. It's a model test to determine the load settlement behavior. It can be used if the strata is uniform. It can determine the modulus of subgrade reaction, to verify, of course, the ground improvement, whether it has been achieved or not, confirm the safe bearing capacity, also performance of highway embankments. So these are typical arrangements for the test. You could have a dead load or you could have anchors. But the test is suitable only for uniform stratigraphy. Since the depth of the test is limited to 1.5 times to 2B, larger size foundations shall not influence the deeper soils. So particularly if there's a looser soil, then you could have some unreasonable results. So the larger size foundation may not be able to be modeled by the test. Footing load test is only one step on the plate load test. This is being used for multi-story tall buildings and all that. Here, this is a photograph of a 2x2 size, 2 meter by 2 meter size concrete block being tested in Noida. Better assessment of the modulus of subgrade reaction. But again, the depth of influence is limited. Here, 8 anchor piles were used. So it's a very expensive test. You have to have anchor pile, large diameter, 500 diameter, 20-meter depth. Similarly, 500-ton capacity jack was used. A test was done up to 240 tons. So it's a very expensive test. Now I move on to advanced testing technologies. Please tell me how much time I have, because I have another 15-20 slides. Electric cone penetration test. I've been talking about it. So here you push the cone at a constant rate of 20 mm per second. The readings are taken every 1 or 2 seconds. This is the what shows you the cone. This is the close-up of the details of the cone. There's pressure sensors and sensor to measure pore water pressure. Data collected is electronic, connected to a computer for data logging. So it eliminates human errors. These are the cones. You can see the porous element. Normally, this is the U2 position just above the cone. This is the standard position of the sensor for pore water pressure. There is also another system in which it is in the cone itself, but not very popular. This is more popular. 10 square centimeter and 15 square centimeter type piezo cones are being used. The 15 square centimeter, again, more consistent results and are used for that. If you want to do a seismic cone penetration test, you would add a seismic sensor. You could also add sensors to measure electrical resistivity or thermal resistivity of the soil. Typical CPT results. So you have cone tip resistance, sleeve friction, pore water pressure, and then the interpreted soil behavior type. I move on to the seismic cone penetration test. Here, what you're doing is you are having a hammer which hits the side of the CPT rig, and it measures. So as it hits it, so this is the sensor here, which you would use to. So it would be pushed to different depths, and so there's a horizontal hammer hitting this, so you get a shear kind of a resistance. Now I move on to pressure meter test. Again, another in-situ test to measure the in-situ stress strain response. So here you have um, uh, the pressure being applied on the sides of the borehole. So it's like expanding a balloon within the soil. Stiffer the soil, the more will be the pressure required to expand the balloon by the same volume. It involves drilling a borehole, placing a pressure meter probe to the required depth, and expanding it. So it measures pressure applied versus volume change. The probe has two inflatable cells, a measuring cell which expands as it is filled with water, and a guard cell filled with gas, which protects the measuring cell from shocks and impacts. So this is a pressure meter test being performed. This is the pressure meter probe. You can see the central portion is expanded. So this is how it will expand in the soil. This is the probe in the unexpanded shape. This is the probe for soil, and this is covered with steel strips for performing test on rock. Typical results of the pressure meter. You have pressure on the y-axis and I have volume on the x-axis. So this would be the field curve, pressure versus volume change. Then there are various corrections which are applied and you get the final curve. You can this maximum pressure is called the limit pressure, and the slope of this pseudo-elastic part of the curve, that gives you the deformation modulus. I then move on to geophysical tests, electrical resistivity test by the weather configuration. You have 4 electrodes at equal spacing. The inner electrodes are the potential electrodes, the outer ones are the current electrodes. You can use the test to interpret the strata using the inverse slope method, as has been done here. So this is the entire cross section of the bridge has been assessed. Electrical resistivity tomography or imaging. This is an advancement in the conventional resistivity testing. So electronically, you acquire the data, and using the software, the various layers are identified. It uses a grid of 50 to 100 electrodes. So resistivity profile, then you can match it with the borehole data. Cross-hole seismic test gives you the various the shear wave velocity and the P wave velocity with depth. So you have 3 boreholes spaced 3 meters apart, and this is the data acquisition being done. And what you get here is your shear wave velocity, your primary wave velocity is what you would measure from the test, and then dynamic Young's modulus and dynamic shear modulus is determined. Various other parameters like the coefficient of uniform elastic compression and shear and all are also you can determine. I move on to seismic refraction test. So here you have an array of 24 geophones are placed along a line, and you would perform the test. So this is being done at Delhi Metro at night to minimize the traffic disturbance. The data acquisition here. So this is the seismic profile which was obtained at that particular location, and the boreholes were drilled at these 2 points, and we could find a very good match here. Do I have a little bit more time for case studies, or should I wrap it up? Well,
how much time you need for the covering case studies?
Another 7 to 8 minutes.
Okay, you have 10 minutes, sir.
Okay. So this is the first case study, industrial sheds at Sonipat in Haryana. 17 sheds were planned in this area. This is a medium-sized project. I have 2 case studies. One is this medium-sized, and another is a large-sized project. So I am taking up only this one shed here out of these 17. So I'm just going to demonstrate the benefit of using CPTU in addition to the boreholes here. So this is shed number 10. I have the borehole data. 2 boreholes and 3 CPTs. The strata interpreted from the CPT. So here in the Indo-Gangetic alluvium, basically we have sandy silt or silty sand to 11-meter depth, and below that we have clay silt of medium plasticity. Groundwater was not there to 25-meter depth. So these are the CPT results. The cone tip resistance, the sleeve friction, the friction ratio, and the soil strata interpreted from that. Interpreted from correlations of Robertson, the SPT has been correlated. You can see an excellent match in the data. Similarly, the undrained shear strength from the test interpreted data is matching with the undrained shear strength from the laboratory. Similar, the phi, and of course, the densities are slightly on the lower side in the laboratory because of sample disturbance. So this is the design profile that was developed, and foundation analysis was done uh, um, for the foundation at 2-meter depth, 3 and 5-meter wide foundations. So first we did the bearing capacity analysis as per IS 6403, and then with Robertson's correlation. Even for a factor of safety of 3, Robertson gives me higher bearing capacity. Then settlement analysis was done again from IS code, classical analysis, immediate plus consolidation settlement, and then Robertson and 𝐏𝐫𝐤𝐻. So you can see here for 2-meter wide foundation, from N values, it is 202 from elastic and consolidation settlement, it is 420. A CPT based analysis from Robertson gives me 1175. So you can see Robertson's predictions are quite high compared to what IS code would predict. Similar kind of trends for 5-meter wide foundation. This gives you a picture of exactly how these various things spanned out. So finally, the designer went for an intermediate value, which was much higher than the IS code values. But since there wasn't enough confidence, they didn't go up to all the way to the Robertson's values. The intermediate values were used. So maybe once the experience increases, people will start using these higher values. So you can achieve substantial savings by that. I move on to the next case study, multi-storied residential complex. So this is a building having G plus 32 floors plus 2 basements. This is coming up in Gurgaon. The basement floor will be at 8.4-meter depth. This is an artist visualization, of course. So here the scope included 13 boreholes, SPT analyzer, then 36 hole penetration tests, and then 2 footing load tests. That's the plan. The investigation being performed, boreholes, the CPT, data acquisition using CPT. So, but here I am just restrict myself to a small zone of these 2 towers, borehole 9 and 10, CPT 21, 25, 26, 37, 38. So these are again the stratigraphy from the boreholes as well as the CPT. Groundwater was at 7.5 to 8.8-meter depth. This is the average CPTU profile, the cone-tip resistance, lead friction, pore water pressure, friction ratio, and then again interpreted profile from CPT, N values, shear strength, friction angle, bulk density. You can see SPTs, of course, there is a very good match. Shear strength also, you can see a reasonably good match. And so this is the constraint modulus, and the OCR, Young's modulus, of course. So this is a footing load test being performed using truss with 16 reaction piles for the footing load test. The reinforcement of the piles was welded over the girder. So maximum load of 450 tons was applied. Dewatering was, of course, done to 1 meter below the ground level. That's a close-up view of the hydraulic jacks. And each reaction pile was designed to withstand a pull-out load of 34 tons. So each load was held till the rate of settlement became negligible. Maximum load held for 24 hours. This is the load settlement curve. So from this, very useful data could be obtained. The ultimate bearing capacity, the measured settlement, modulus of subgrade reaction, E value, everything could be determined from here. This is the design profile. I'll quickly go through this. The MV was interpreted from the constraint modulus. So various analysis, as I told you, was done for 1.5, 10, and 20 meters wide square footings at 8.5 meter depth to calculate the bearing pressures at 250, 400, and 500 kPa. So these are the values you can see. There is a very, the Robertson gives you the best results matching with the footing load tests. That is the benefit of the CPT. Similarly, you can see that you get a very good match when you compare the footing load test with the CPT. So with this, I conclude. For small, medium, and large size projects, the scope should be carefully planned based on the project requirements. In-situ testing using advanced testing technologies is becoming important. And conventional boreholes with laboratory testing is now being taken over by in-situ testing to generate site-specific results. CPT is now becoming very popular, being used on several projects. So let's go for it. With better understanding in the technology, increased use of geotechnical investigations, geotechnical engineers can ensure reliable and economic foundation designs. BIS has recognized the importance of CPTU. A new code is coming out very soon on the CPTU. Thank you very much. I'll be happy to take questions. Just a reminder, geotechnical engineering is a science, but it's practice and art. So I'd encourage all of you to master this art. Thank you very much.
Thank you very much, sir. It's actually a very comprehensive presentation, primarily covering the guidelines for different projects of different scales, and also briefly introducing different investigation tools from basic SPT to the advanced CPT and geophysical techniques. It actually sets a stage for this lecture series, and we'll be taking up in the subsequent lectures the in detail each and every tool for investigation. Thank you very much.
Sir.
Yeah, thank you.
I do hope that it served the purpose which you had planned.
It is indeed, particularly the guidelines, the initial slides for different projects should be the number of boreholes, size of the boreholes, depth of the boreholes, and so on. Thank you so much. Now the floor is open for Q&A session. I request the participants to provide your questions in the chat box or raise your hands. Before we move on, we have Professor Anbalgan from IISc Bangalore who attended this lecture.
Hello, Professor Anbalgan.
You can unmute all of them. Professor Anbalgan, sir, can you hear us? Okay, we will move on to the Q&A session. Participants, both in person or online, you're free to now provide your questions and answers.
Yeah, actually, you have to unmute me to talk. Now you are unmuted. Hello,
Professor
so good evening, all of you. So just I want to listen the practitioner perspective on so the planning of this one. That's why I was participating in the lecture. So anyways, Ravi Sundaram covered all the aspect. So it was a very good initiative by the IIT Tirupati. I appreciate really the Janaki Raman and so his team to take up this important aspect because you have to learn properly geotechnical engineering to avoid any disaster in the civil engineering. Okay, so that is my observation. Sorry, I could not able to talk to you because you are not unmuted mic in the beginning, even though both of you are talking. Only now, just now they unmuted the mic. Okay, thank you, Janaki Raman.
Thank you. Sir, for your information and for the information of others, Professor Anbalgan will be the next speaker on SPT in our lecture series. It will be somewhere between second week or third week of September, depending upon his availability. Thank you.
Hello, Professor Anbergen. Honored that you attended my lecture.
Thank you, thank you. Anyway, you are from the industry, so your experience always matters for all academicians. So that first starting with industry is always good, actually.
Okay. Now we on to the Q&A,
Ravi
please.
sir, good evening. Thank you for an excellent lecture. Ayodhya here.
Oh, hello, hello.
Yeah.
Great to connect to you.
Yeah. Really, we are thankful to you for accepting our request and gracing the occasion. And then, as usual, a wonderful lecture. Always pleasure listening to you, and it's a learning experience for us. Somehow, when
Thank
I
you.
logged in, it has taken the IGS main body account. So, in a way, IGS also has witnessed your lecture.
All right.
Yeah. That's why my name is not coming in the participant. Thank you, sir. Thank you. We would have loved to have you in person, but I looking forward another occasion.
Oh, yes, I'd love that.
Yeah. We'll try to have you.
Tirupati is always special.
Yes, sir. Thank you. Thank you very much, sir. Thank you.
Thank you.
Thank you, Anbalagan, for joining. Thank you.
Anybody in person here, please feel free to talk. There are no questions. Either you understood completely or nothing.
That's the risk.
Raviji, good evening. This is Murli here.
Hello, Murliji. How are you?
I'm good. Thanks for delivering lecture. Excellent.
Thank you. I hope you
covering
liked it.
everything. Yeah. Wonderful. Thank you.
Yeah, I think it should be a more interactive session. Should be from your side. It's only the professors talking now.
Hello.
Yeah, please.
Hello, sir. Suhas here. Ravi, sir. Good afternoon.
Yes, Subhash.
Sir, I have a question regarding the electrical resistivity imaging, sir. So I just wanted to ask you whether the ERT test or the electrical resistivity imaging test, these are two different tests, or this is the one test which gives the idea about the imaging process, sir.
See, the imaging is a digital thing. The concept in both the tests are the same. You pass a current through the ground, and then you measure the resistivity, and from the resistivity, you would get an idea of what type of soil it is. You could also make an assessment of where the groundwater level is. So the traditional method of doing the resistivity test was you had 4 electrodes, and then you would have different kinds of electrode arrangement for different applications. If you are looking for groundwater, you would use a Schlumberger array. If you are looking for a geotechnical application, you would use it for use a Venner array. There are various other kinds of electrode spacing also available. So depending on the application, you would use the appropriate test method. Now, with computerization and modernization, digital data acquisition becoming mm, a big thing.
Mhm.
So
Mhm.
ideally, I would like that if I have a software and I plug my electrodes through a system, a data acquisition system, and analyze it for different combinations, and then I'm able to get some nice looking colored graphs
Mhm.
identifying the various layers. Uh,
Yeah.
so, it is only an upgradation.
Mhm.
The concept is the same.
Understood, sir. Sir, and one more thing, sir. In like when even in the ground itself, sometimes there is like the space constraint, sir, for doing the four-Venom point of method. So there is a method like a space constraint. Like you can't have a 15-meter, 30-meter of clear stretch in between 2 points. So
Mhm.
what can we do in that situation, sir? As per the client's requirement, if he wants to conduct an ERT test on that particular location and there is no space available for doing the ERT test. So what can we do? What can we suggest to the client?
See, this is very often a problem. In that case, you'd
Mhm.
probably have to think about doing a CPT. And the cone,
Mhm.
you could have a sensor that measures resistivity. Hmm.
Okay, sir. Understood,
Uh,
sir. And sir,
that Yeah,
yes.
these kind of equipment, I am not sure if it is available within the country. Although seismic
Mhm.
cone is available,
Mhm.
resistivity and thermal conductivity, electrical resistivity and thermal conductivity sensors. Whether any company has it in India, I am doubtful. Uh,
No, sir.
Although
There
internationally,
are. Sir. I guess there are some like manufacturers and the third party consultants from the Netherlands. They are
yeah,
like
yeah.
they are providing the services, sir.
Internationally, there are, but I'm talking
Yeah.
about whether availability in India. Mm.
No, sir. There are third party people who does it for the international companies, sir.
Yeah, but then they would come from Netherlands or
Yes,
Europe or
sir.
somewhere and do it.
Absolutely, sir. Absolutely.
Yeah, that
That's
would obviously increase the cost. Mm.
yes, sir. Yes, sir. Yes,
Now,
sir. And mhm.
since seismic cone is available with few companies in the country at least, so the cost of
Mhm.
seismic cone test is not very expensive. Hmm.
Yes, sir. Yes, sir.
It is affordable. But if I were
Mhm.
to, have a, uh, team which would come from abroad and do the test, obviously all that adds to the cost.
Absolutely, sir. Absolutely. Thank you so much, sir. Thank you.
But
Thank you so much.
these things are coming, and in the next few years, definitely there will be agencies in India who will be able to do these kind of
Mhm.
tests.
Yes, sir. Yes, sir. Absolutely, sir. Thank you, sir. Thank you.
Welcome.
No questions from our side? Okay, participants online, please feel free to interact with the expert. We still have some 10 minutes time. Okay, then yeah, thank you. I see no questions from both online and offline. Then if you have any questions, we can directly contact the expert. Yeah, there is some question from anonymous participant. I read out to you or anonymous participant. So whether geophysical methods will be more accurate compared to SPT, CPT, pressure meter test? That is question number one. Question number two is, while comparing the pressure meter test with the dilatometer test, which one is best?
Okay, so the second question first, pressure meter and dilatometer. Basically, it gives you very similar parameters, and both are comparable and you know, a dilatometer as a test is easier to perform. It measures your change in diameter, whereas a pressure meter measures change in volume. So depending on your application, settlement estimates using both pressure meter and dilatometer, they give you comparable results. So there is nothing to vote for or against the two methods. Now I come to geophysical tests. Geophysical tests are indicative. They only give you the layering, at what depth there is a strata change, what is the type of strata, whether it is sand, silt, or clay, or rock, or things like that. It gives you the that kind of it does not tell you whether the soil is very strong or from the geotechnical perspective. It does not tell you. I cannot use a geophysical test to maybe calculate a bearing capacity or a pile capacity. So what you get from the geophysical test is a continuity of strata, which you can determine like from seismic refraction tests. Geophysical tests can help you do your earthquake stability seismic tests, like your cross-hole seismic, down-hole seismic, seismic cone penetration test. So it gives you liquefaction input for your liquefaction analysis. The resistivity testing, of course, it has its own applications. Again, determining layering, also determining groundwater and other applications. But these are not a replacement for the borehole. The CPT supplements the boreholes. Pressure meter supplements the boreholes. But as far as geophysical, it has a different application. I hope I am able to explain.
Yeah, that was anonymous participant. I don't know the name. It's not displaying. I hope those two answers will clarify.
This question was not in the chat box also.
It's in the Q&A session.
Okay.
There is a different one actually. It's not in the chat.
Oh, I see.
It is a separate module that is Q&A. It is reflecting.
Oh, yes, yes, Q&A.
Okay, he replied yes, sir. So any other questions?
It shows anonymous participant. I hope whoever you are satisfied with the result. You could probably give your share your name with us so that we know who you are.
Other same from the same participant question. What type of foundation you guys suggested for Ram Mandir? Since steel cannot be used in temple construction, does that make it more difficult?
Excuse me, I can't hear you. Could you speak louder?
Yeah, that is me only.
Okay.
Another question from the same participant is, what type of foundation is suggested for Ram Mandir? Since steel cannot be used in the temple, does that make it more difficult?
To discuss Ram Mandir would require one more lecture like this, but just I will give you brief this thing. Actually, the challenge in the Ram Mandir was that steel cannot be used. So most civil engineers are used to using reinforced concrete. And once you say that reinforced concrete cannot be used, then civil engineers feel very vulnerable. That's really so. what we had to do, we had to look at other options because it was granite masonry which was used. You might just a minute. So what we had done there was it was excavated down to 12 meters, 12 to 14 meters. The Garbhagriha was 14 meters because that was the thickness of the filling there. And then the excuse me. And since the filling was from of various old materials, they even found a lot of artifacts. And all that. And from such a deep level, the construction was made.
Sir, I think we will close the session. We would like to propose a formal vote of thanks.
Thank you very much.
To the participants.
There is a question here on procedure for SPT energy measurement. I think Professor Anbergen will be taking that up in his lecture. So I am not going into that. With that, yes.
We'll conclude the session, and the participants, you're feel free to send emails or to us so that we will pass on the same questions to the speaker for clarifications later. Thank you for joining. Mr. Darshan will provide the vote of thanks.
Hello, everyone. Thanks to all the participants for your engaging the question and discussions. And once again, our heartfelt gratitude to Mr. Ravi Sundaram for patiently addressing them and enriching today's session with such a valuable insight. On behalf of the IGS-IITT Tirupati student chapters, I take this opportunity to express our sincere thanks to our speakers for sparing times from their busy schedule to deliver today's lectures. Your insights have truly broadened our understandings, will certain inspiring future discussion and application in our respective fields. Thank you to everyone who joined us online and to our organization and technical terms who made this event possible. To stay connected with IGS-IITT Tirupati student chapter for future event, for regular update and upcoming lecture and events. Please follow our official page on LinkedIn, YouTube and Instagrams. With that, we formally conclude today's lectures. Thank you all once again for beginning with us. We look forward to your participation in the upcoming lectures on this series. Have a wonderful evening ahead. Thank you, everyone. Now we are taking a picture.
Thank you for the opportunity to give this lecture. Thank you.
Yeah, please send us the feedback so that we can improve if it is required, or you're free to even suggest the topics related to ground investigations. We'll try to contact eminent speakers in that context. Thank you all.
Thank you, Ravi sir. We'll catch up. Thank you, Ravi sir. Thank you very much.
Thank you very much. I'm now leaving this call. Thank you.
Thank you. Thank you, student team, and thank you, Janagi. Great.
Sir, now we are taking for pictures, so we request you for turn on video.
Our video have been locked. We are unable to share the video, and just see Professor Ravi sir is there. Because
Ravi sir is here.
Yeah, for a group
participants
photograph.
online, kindly open your video so that we can take a snapshot. Sweet memories.
Just 1 minute. Am I visible?
Yes, you are.
Okay, great.
Nice to see you. It's been a long time.
Yeah, same here, sir. Same. See you here. And I came to Delhi for 15 days, but it was very hectic. So in July, first 2 weeks.
Okay.
Yeah. So next time when I come, I'll just inform in advance.
Give me a call. we
Sure.
can maybe meet briefly.
Sure, sir. Sure, sir. Thanks. Hi, Falak. Nice to see you. How are you?
Hello, sir. So I'm fine. So how are you?
I'm fine, beta. Fine. Good to see you.
Thank you, sir. Thank you, sir.
Thank you so much. Have a good evening. And we'll look forward all of you in the future sessions. Thank you all.
Thank you.
Thank you, sir. Bye. Thank you, everyone.